So our next speaker is Erich Kobler. Erich is a lecturer at the Institute for Machine Learning at the University of Linz. And he will be talking about his work entitled Dealing with Image Reconstruction, Deep Attentive Least Squares.
Thank you for the kind introduction, and I really appreciate the previous talk because this is kind of problems that are very interesting to us because 1D, 2D images are quite well solved with AI problems nowadays, and when it comes to 3D or in this case 4D imaging, we really have to think a bit more and get the best of both worlds, right? AI and physics-based modeling or model-based reconstruction. And with this talk, yes, thank you. With this presentation, I will maybe show you an approach that I also tried a bit to stand in the center here that could work in this field. Okay, so let me start. My work has been focusing a lot on inverse problems and reconstruction projects for that, and basically the goal is always the same. We want to estimate something unknown from some measurements. And in this talk, I use X for the unknowns and measurements Y. And throughout this talk, and actually from my research, I always was pursuing like a Bayesian approach, where we want to find a posterior. So given the measurements, I want to find the probability of my reconstruction. It's by Bayes rules. It's proportional to the likelihood times the prior, right? And often we know quite a lot about the physics, and we can model this typically, or we do model this. And in this case, I know the image formation process here. We have potentially a non-linear operator or a linear operator plus some additive noise in this case, but it can look different. For instance, this could be noise or Poisson noise, and the second term is this prior. And here I've not written so much because this one is typically a bit harder to model to get really a model that grasps the complexity of all the images that we can generate. Good. So let's give some examples here for this setting. Image denoising, it's quite forward, right? This linear operator, or this operator is the identity, and the noise is just Gaussian in this case. And here we have super resolution. We have convolution with a blur kernel downsampling and get these images. So this is like, sorry, the operator is actually going from this side to that side for the arrow. Still, we can have some noise. Same thing, other way around, right? We have some CT scan, so some body. We do CT measurements, and we want to reconstruct essentially these attenuation coefficients of the body. Good. Next thing is the same. So one of Florian Nies, probably it's not yours, but from your data set. Here we have some measurements of the MRI device, and we want to recover these images, and we have some coil sensitivity, the Fourier operator, and some mask measurements in the celerity setting. So you see, we can formalize many problems in this field, and the question is, how can we do this efficiently? So what we've been doing was a lot working this so-called variational approach, and here we want to find a solution x hat of this problem where we want to maximize the posterior. Okay, so the probability of the images should be maximized given the data of that image. Good. So we can decompose this, and this is equivalent to minimizing this negative log function here, and then we see this log likelihood corresponds to the data fidelity, and by assuming the simplest scenario, so we have additive Gaussian noise, we end up with this function. And this function is very nice for optimizing, so let's stick with that for now. As I've said before, for the prior, we don't know much about, actually. We don't want to model too much because all our models are mostly a bit off. So this corresponds to the log prior. So let's look a bit into history. So quite a while ago, actually, the first one prior that has been interested or regularized is this well-known Tikhonoff regularizer, and I want to focus here a bit on the structure of this formula. Right? We have this regularizer function, and we can write it like this. So it's a L2 squared norm of some operator W applied to X. And this operator can be wavelet transform, Schiller transform, just convolution kernels or whatever. And this is the more important part for this talk, what is on the right-hand side. So we can write this as a scalar product of this operator and some activation function applied to that. And then we sum over the entire image on this, okay? So for every pixel, we give the same weight. Or we apply the same model everywhere. Same can be done for another very famous regularization function, which is the total variation regularization. In this form, the isotropic one. So we have a 2-1 norm, which essentially boils down. We have gradients in horizontal and vertical directions, square everything, take the square root, and still sum up over the entire image. So we do at every position the same thing. Good. Then there has been extensions, actually also more than 10 years old. Fields of experts, actually 20 years almost, sorry. Where it's a generalization, we can have now arbitrary convolutions or filters or operators here. We can have some arbitrary potential functions, but we still do the same thing. We apply the same model everywhere, the same. Okay, so just analyzing a bit how we can compute solutions by this term of priors that we use. The first thing, the Tikhonov is quite nice, right? Because at the end of the day, if you assume our likelihood from before or data fidelity, we essentially need to solve this quadratic problem. And all of you who are in Reconstruction should be very happy with that, because this we can do easily, right? Cool. So do you know the solution? Because I want to uncover it now, right? The solution is just, I need to compute this matrix. So derive this, set it to 0, and this will be the solution. So here we have this matrix. So if H and W are quite nice, we can compute this inverse, and then we can nicely solve this. So this changes a bit for the total variation of fields of experts, right? Because here, this is not quadratic anymore, necessarily. So we have to do some iterative approaches, right? So it's not like we can directly compute this closed form. So for instance, we can do a proximal gradient descent or whatever, whichever method you like, and depending on the structure that your prior has. Okay, good. So since I was dealing a lot with machine learning and AI, of course, the question is, when we have a look at these models, what could be learned from data, right? So now we specified somehow the hypothesis class of these models. And obviously for Tikhonov, easy thing would be, okay, I want to somehow maybe learn the noise model or the operators. And for TV, with this addition, it can learn also these parameters, the operators and the functions. But also we could use in an unrolling setup, like we've heard before, learn also the step sizes or additional parameters, like this weighting here of the data fidelity. Okay, so far so good. Everything quite well understood, right? Nicely motivated and some math background. So actually, 6 years ago, sorry, we introduced another variant of total variation method, which is motivated the same way. So we do at every position the same thing. We have some linear operators or nonlinear operators in this case, and apply a potential function. We call this total deep variation because it uses a deep network actually to transform the images into features. Looks like that. Yeah, it's just a unit kind of approach. Works quite well, but still we do the same thing as before. Then there have been nice extensions like the plug-and-play approaches, where you essentially try to learn a denoiser network, and then you say, okay, this denoiser network essentially solve a denoising problem, and then you can use this as a more or less plug-in replacement of this proximal operator in various algorithms. Good, and there has been extensions also like a proxtrnet, just to freshen you up a bit, where we can have a tighter theoretical connection here. Good, so this is the background. So now let's motivate you a little bit. This dealing approach that I want to highlight in this method is, as I've said, we have this kind of structure. So the goal of this talk is we want to have this first principle basic models that we want to learn. And let me motivate the next step a bit with this image, right? So this is the famous Barbara image. And if you look at the different structures here of the image, they are quite different, right? So it's not the same everywhere. Here we have more like homogeneous regions. Here we have a lot of edges here as well. So it would make sense that we don't use this one. So do at every position the same thing in the image. And that's what we essentially do. Okay, we say, how far can we get with our modeling approach if we use the simplest form here, so just quadratic potentials, and we change how we weight this models. Okay? And then you immediately see what we essentially do then here. We use simple priors in this case, but we change the metric. So you can ignore this square. It doesn't really matter. It's just an implementation issue. So we did it like that, but yeah, it doesn't matter. Good. So that's how we define the steel regularization. So simplest model, quadratic functions, because we can get simple solutions to these problems, and we change the metric how we measure these functions. So as I motivated, this role of these local weights is essentially to account for the local structure of the image content. And how do we utilize this? The best case would be that someone gives me a nice image of the ground truth. This is not possible typically. That's why we do the best thing we can do. Okay, we work with an estimate that we have so far. And then we use some model, so in this case just the CNN, to extract these local structures. So why do we use a CNN here? Because it has the intrinsic property of locality, right? And we want that this is somehow reflecting what we see locally in an image. Good. This is just a two-layer neural network with spline activation functions. And this was work done with Michael Anza and colleagues. So we had a focus on splines a bit here. Good. So what we end up in the day with this method is we want to find a fixed point to an update operator, and we start with an initial image. In this case, we simply took just the constant 0 image. And what this operator is doing, essentially, it solved this quadratic problem, and the metric is generated by the previous iterate. Okay? And this boils down to solving this problem. And all of you are happy because solving these problems is quite easy, right? So we only need to invert this matrix AK. And we can do this efficiently with so-called conjugate gradient methods. Okay? And this has the same structure that I had on the previous slides. So for those who like box plots, so this is more or less the same, just in nice colors. And how do we train this? Right, that's a very important question. So we train this for just image denoising and then apply it to various different problems. Let me walk you through this a little bit. So this is the loss function of the training. This is more or less the output of the network. So we want to train it that it matches the ground truth in an L2 sense. And we also train it that these mask networks, right? So this is the output of this local adaptivity setup converges. So in the best case, if this converges, this vanishes, this part, right? Last mask versus second last mask, if it's always the same, this loss becomes 0. And then we have some regularization of the weights. So what is this K out? So this is the number of steps that we do. So right, I said we solve a system of equations, then we get a new initialization, update this local conditioning, solve another system of equations, and we do this several times. And as you see, we can do this randomly, actually, in the setting, this K out from 15 to 60 steps. So do you think this is fast? No, right? Because you've heard about unrolling before, right? So we do this 15 to 16 times, and I have to backpropagate 15 to 16 times for a conjugate grading algorithm, which has another 15 to 20 iterations in between. So I do this, go back, this, go back, okay? But in fact, we don't have to do that. That's the nice thing. Because what we utilize in this training process is we utilize something which is Jacobian-free backpropagation, which is very nice because we can just solve the system forward, can ignore everything what we've seen before, so all the gradients, etc. And then we do one step where we track gradients, and then we just backpropagate through that one step. And it has shown, actually there has been some evidence in literature, that this already is a very good approximation to the gradient, and I will convince you that this works also here. Good. Then we only have to backpropagate through one of these GG algorithms, and this can also be done by just solving another CGG problem. Okay? So, good. So we can learn everything efficiently, and we just have a handful of parameters, something like that. So let's see how this parameter looks like. This is this mask network. This is the intermediate spline functions that are used in this network. And this is spline functions of different kernels, so operator that has been learned. So 5th kernel, 15, 15. One side note, they are all 1 at 0. Do you know why? Do you have a guess? because this is the output of the mask metric. Just let me go back a bit. So right, this is the metric. And if we know nothing about a problem, probably should set the metric to 1, right? So we do everywhere the same thing. That's why this is 0. So having at 0, 1 is already a good starting point, and then this is refined by the model. And by the way, this is for different noise levels. Sorry, this is for noise level sigma 5, 15, 25, and this is the different filters. So here are the filters that have been learned, so the linear operators. And you see it's like all kind of forward differences, diagonal, whatever, higher order filters like Laplace filters and so on. So, okay, what we get here, or what I want to convince you, is that this model learns low-level features. Just a couple of edges that it wants to penalize. So how does this look like initially? So what I'm showing now is here is the estimate of an image. Here is the average of all the masks for all these operators. And here is somehow the convergence plot and also how this performs to the ground truth. This is after the first step. You see Tikhonov regularization, right? Everything is very blurry, quite a heavy regularization, but we do get already an estimate what this local image content should be. Good. Second step, it's getting better, right? These edges form out, third, 10th, 40, and so it's nicely converged. So what popped a bit into my head when I saw this first, I noticed this stuff, right, on the boundary. It looks a bit strange. And I always thought this like a bug, but now I realize it's like a feature, right? Because what we typically do, we have a boundary condition there. And what is typically implemented in Torch is that we fill it with 0. There's a strong edge there. So it makes sense that we turn down this weights there as well. Okay, good. Nice thing is now we have a very simplistic model, and we get actually quite close to very similar models that just deep convolutional neural networks. And what we do is just, okay, we have this 2-layer neural network that predicts the masks, and we solve a sequence of quadratic problems. Good. So, yeah, I skipped that. Actually, let's see, how much time do we have? Yeah, probably I should skip something. Just a visualization of all the stuff. And now let's have a look at super resolution problem. I jump to this table here, and you see that with this approach, we actually get quite similar results to previous approaches as before, but we have this very nice interpretation. And one column I would like to highlight, this is the column that deep neural networks have been trained on, and you see they perform the best. But as soon as you change the operator a bit, obviously the performance degrades. And with this simplistic approach, we can easily adapt to new settings and new acquisition processes. We can show some nice math, and we can see that this intersection of the kernels that we need for existence is actually given, because most of the inverse problems don't have a 0 frequency at the DC component, but I skip over it a bit. And we can also have a nice thing, because it turns out that this mapping that we learn is most of the time contractive, so this means it points to the same solution. Okay, good. So let's have a look at this, how this looks in practice. Again, there's a super resolution problem, so it's an IL+ problem. We start with the initialization that the model has been learned for image denoising. Then we see you get this trajectory. So now we start with uniform noise, get this trajectory. Gaussian noise, this trajectory. Then we do the adjoint initialization, get this trajectory. Then we start with the ground truth and converge to this point. So this is empirically actually quite nice that this method converges to a kind of a stable fixed point, which we like very much. So let's have a look at MRI. So this is not clinically validated or any kind of thing. We just used 50 samples from the fast MRI dataset and evaluated how this method trained on natural images works. So after the first step, second step, third, 10th step, 20, and so on, we nicely converge. Here you see an estimate of the edge maps. As I said, it uses first principle, like edges, corners, whatever, of the image to guide this reconstruction problem, and we still just use quadratic problems, solve quadratic problems in this sequence, which is quite nice. And also from this, we've seen get quite similar performance to what we've seen before. And we did one experiment in a paper which I want to point out because of the previous talk. So this method was the only one that we could scale to 2K by 2K images for MRI reconstruction, because it didn't run out of GPU memory, but it's just applying it naively. So this could be a potential fit for this kind of big data. So the last point for my presentation is how we interpret this, right? Because what we do at the end of the day is just we solve a quadratic system of equations. And this means that our solution is just a linear operator applied to the noisy data that we get, right? Because why is this noisy data? Our solution is this, so this is the solution. And now the question is, how does this linear combination look like? And it turned out that we can have a look at just on one row of this operator, and this row corresponds to this pixel. And then you see, okay, our model just learned to average following this kind of edge here, okay? So now I use a different pixel, I use this pixel. The operator is just averaging along this structure here. That's why we call it attentive, because it evolved due to solving this masking and solving quadratic problems. At the end of the day, we just learn averages of the surrounding data. And if there is no structure, we just average above everything that is around there. Okay, good.